Hello my friends and welcome back to the You Can Do TV channel, TES. Galvanized, a leading name in steel structure solutions, operates a state-of-the-art pole manufacturing facility that specializes in the production of galvanized steel poles for power transmission, street lighting, and telecommunication applications. The process begins with high-grade steel plates being cut into trapezoidal shapes using CNC plasma cutting machines. These plates are then bent into polygonal or conical sections through hydraulic bending machines. Each section is precision welded using automated MIG/MAG welding systems to ensure structural integrity. After welding, the poles undergo deburring and grinding to smooth the seams, followed by dimensional inspection to verify straightness and taper accuracy. The poles are then moved to the galvanizing area, where they are submerged in a series of pre-treatment baths to remove rust, oil, and mill scale. After cleaning, the poles are hot-dip galvanized in a molten zinc bath at around 450 degrees Celsius to provide corrosion resistance that meets ASTM and ISO standards. Post-galvanizing, the poles are subjected to straightening and final inspection, where critical parameters such as wall thickness, coating adhesion, and surface finish are checked. Additional fittings like base plates, arm brackets, and climbing steps are installed based on customer requirements. The poles are finally packaged and dispatched for shipment. Galvanizing's integration of automation, strict quality control, and adherence to global standards has made it a trusted supplier across the Middle East, Africa, and beyond, with capacity to produce thousands of poles monthly in various configurations and heights up to 45 meters. Metal Pole is a leading manufacturer of high-quality steel poles, offering tailored solutions for power transmission, lighting, and telecommunications. The process begins at the design, where engineers use CAD software and structural analysis tools to develop custom solutions based on client specifications and applicable standards. Once designs are approved, certified structural steel sheets are selected for production. These sheets are precision cut, then bent with hydraulic presses to form polygonal or round tapered shapes. Automated welding ensures uniform, high-strength longitudinal seams. Each pole undergoes strict quality control, visual inspections, dimensional checks, and mechanical testing to verify structural integrity. Finally, the finished products are bundled and shipped. With in-house engineering and advanced manufacturing, Metal Pole delivers reliable, custom-built steel pole solutions worldwide. Metal Pole steel poles are used in power transmission, urban lighting, telecommunications, traffic surveillance, sports fields, and billboard installations thanks to their high durability and flexible design. At Gerdo Duluth, grinding balls are produced through a fully integrated process, emphasizing precision metallurgy, material integrity, and operational safety. The journey begins with 98% recycled scrap steel, sorted for optimal chemistry. This material is melted in an electric arc furnace, EAF, refined in a ladle station with custom alloy additions to meet hardness and wear resistance specifications, and cast into billets via a continuous caster. Billets are hot-rolled in precision rolling mills to create bar stock with tight dimensional tolerance and uniform concentricity. These hot-rolled bars are shipped to the Duluth facility, where they undergo induction heating to achieve optimal forging temperature. The heated bars are sheared to length and transferred to a forging station. Using primary and secondary dies, the material is forged into spherical balls. Rotating dies refine shape and remove flash. Post-forging, the balls undergo controlled quenching, air and water, and tempering to achieve final mechanical properties. Each batch undergoes manual and automated inspection, ensuring consistent quality. Final products are packed for global delivery to mining customers, where they're used in ore grinding mills. The result is a durable, reliable grinding media product, forged from scrap, engineered for performance. Imathia Construction plays a critical role in the Haramain high-speed railway project, focusing on advanced track construction technologies. The process involves three primary components: high-speed concrete sleepers, rail welding, and ballast laying, executed with precision engineering and mechanized systems. To produce sleepers, Imathia built an on-site high-capacity factory using a carousel production system. The process begins with inserting steel reinforcements into molds, followed by concrete pouring and vibration. The molds enter curing chambers for 24 hours, after which pre-stressing is applied. Fastening systems are then mounted. This line produces over 2,000 sleepers per day. Rail bars arrive in 25-meter lengths and are flash butt welded into 300-meter sections at a stationary welding plant. The system performs up to 110 welds daily. These long rails are loaded by gantry cranes onto rail-laying trains for direct site installation. Ballast is processed from selected quarries near the corridor, meeting stringent high-speed rail standards. Crushers and sieving equipment produce up to 5,000 tons per day. Hopper wagons transport and distribute ballast along the track. Turnouts, some as long as 200 meters, are pre-assembled from steel rails and custom sleepers, then installed by mobile cranes on special platform wagons. Track alignment is achieved using tamping machines to compress ballast under the sleepers. Ballast regulators and stabilizers finalize leveling and geometry. On-site aluminothermic welding ensures seamless rail continuity. Through mechanized systems and strict quality control, Imathia achieves 27 kilometers of track laid per month, a global benchmark in high-speed railway construction efficiency. Behind every turbine, oil rig, or submarine lies forged steel, and this is how it's made. At Francini Acciai, it all starts with top-grade steel ingots from European mills. These giants are cut using 20 powerful saws and an oxy-fuel machine, then prepped for open die forging. Inside a blazing hot forge, 10 furnaces heat metal up to 1,150 degrees Celsius. Massive presses, up to 8,000 tons, reshape each piece with precision. Manipulators handle parts weighing up to 100 tons. Its raw strength meeting high control. The scale is jaw-dropping. The precision, relentless. No two parts are alike. Each forging responds to a unique combination of heat, force, and geometry. Heat treatment follows. Mobile furnaces on rails and quenching tanks. Water or polymer, stirred by adjustable propellers, ensure uniform structure and hardness. Some forgings stretch 24 meters long. Machining comes next. Vertical and horizontal lathes. Milling. Drilling. Everything CNC controlled for perfect tolerances. Surface quality is inspected using magnetic particles and dye penetrance. Ultrasound checks internal integrity. Brinell tests verify surface hardness. Even destructive tests are done in-house: tensile, impact, microscopic, and spectrometric analyses. From shafts to rotors, parts are certified by global agencies: ABS, DNV, Lloyd's, and more. It's not just steel, it's trust, tested and proven. Watching this, it's like seeing molten potential turn into industrial backbone. Step by step, a massive Kaplan turbine, designed for low-head, high-flow hydropower applications, is transported as a convoy exceptionnel. With its adjustable runner blades and high efficiency, the turbine is carefully secured on a heavy-duty trailer. Escort vehicles guide the load along pre-surveyed routes toward its installation site at the hydroelectric plant. CKD Blansko Small Hydro delivers complete EPC solutions for small hydropower plants, with full control over each technical phase. The process begins in the design department, where hydraulic modeling and mechanical layouts are optimized according to site-specific flow and head parameters. The technical and production engineering teams then develop precise manufacturing plans for turbine components. Kaplan and Francis runners are fabricated using high-precision CNC machining and advanced welding techniques. Critical dimensions are monitored throughout production, and all components undergo strict in-process quality control. Pre-assembly is performed in-shop to verify alignment, tolerances, and mechanical fits. Factory acceptance testing, FAT, ensures full functionality before shipment. CKD coordinates specialized transport logistics for heavy components, followed by on-site erection, alignment, and hydraulic testing by experienced installation teams. The final stage includes commissioning, operational fine-tuning, and staff training to ensure long-term reliability and efficient plant operation. With its own Water Machinery Research Institute and decades of expertise, CKD Blansko delivers custom-tailored, high-performance hydroelectric equipment built to operate with precision and endurance across varying flow conditions. Out with the old, in with the new. This is how a hydro turbine gets a second life. Workers dismantle the massive runner, cutting each worn blade with fiery precision. A brand new stainless steel unit is hoisted in, perfectly aligned, then bolted into place. Industrial renewal in action, loud, heavy, and seriously satisfying to watch. CKD's production plant specializes in large-scale component manufacturing, handling parts up to 240 tons and 15 meters in diameter. Processes include manual, semi-automatic, and automatic welding, all meeting standards. Quality control involves dye penetrant, magnetic particle, ultrasonic, and X-ray testing. The facility offers heat treatment, precision machining, and maritime packaging, supporting global transport by truck, rail, or sea. Big machines, bigger goals. Here's how FLOVEL powers hydropower. The expanded facility machines components up to 8,000 millimeters in diameter, thanks to high-capacity rotary tables and 7-axis systems. Complex profiles are handled with 0.001 degrees indexing precision. Assembly, quality control, and performance testing follow strict protocols to meet global hydropower standards. It's all built to power sustainable progress. Before the water flows, the metal must be forged. This is the heart of turbine production. Giant components arrive and are machined with CNC precision. Welders shape spiral cases and runners, while robotic arms assist with heavy lifts. Each unit undergoes pressure testing, dynamic balancing, and final inspection before shipping. The shop hums with focus. This isn't just manufacturing, it's energy engineering. You can almost hear the future in motion. Standing here, you realize, every bolt, every weld, carries the force of rivers and the trust of nations. Turning raw materials into clean electricity, this is the journey of hydro engineering. At FLOVEL's factory, production starts with massive turbine components, machined, balanced, and aligned down to the millimeter. Technicians assemble rotors and stators, testing torque and efficiency at each stage. Control panels are wired in-house, and full systems undergo model testing before dispatch. Graphite isn't just pencils and electrodes anymore. In this factory, it's engineered into something far more advanced: tubes that resist pressure, chemicals, and time itself. Starting with synthetic fiber and ending with real-world durability, this is graphite redefined. Production begins with extrusion of raw synthetic material into rods and tubes. These are then cut, pressed, or machined using CNC vertical turning centers, hydraulic presses, and precision tools. Specialized assemblies like vertical tube bundles are crafted with extreme care, ensuring structural integrity. Each piece goes through impregnation and curing to boost chemical resistance. Leakage tests, tempering, and strict QA protocols follow. Technicians insert graphite sleeves by hand, a delicate job requiring focus and experience. Final inspection includes dimensional checks, leak verification, and batch marking. Before dispatch, parts are carefully packed with shock watches and labeled for safe transit. This isn't just manufacturing, it's engineering for the most demanding industrial environments. The MRT SSP line project employs advanced engineering techniques to construct both elevated and underground railway infrastructure across a 38.7-kilometer alignment. The elevated sections use segmental box girders, springs, which are modular precast concrete components. Production by forming steel reinforcement cages that are placed in molds. These are then filled with concrete, vibrated for compaction, and moved into curing chambers. After hardening, each SPG, marked with a unique serial number, is removed, stressed, fitted with fastening systems, and transferred to stockyards. The carousel-type production system enables the factory to produce over 2,000 high-speed sleepers per day. Underground sections are excavated using tunnel boring machines, TBMs, which bore through complex geological layers like Kenny Hill Formation and KL limestone. TBMs maintain precise tunnel geometry and minimize surface disruption, enabling efficient tunnel advancement in densely built environments. Rail installation is performed using 25-meter steel rails, imported and welded into 300-meter lengths at an on-site stationary welding plant. These long welded rails are transported by gantry cranes onto a specially designed long bar train capable of laying up to 9 kilometers of track per operation. Ballast, produced from high-quality quarries, is laid and compacted using tamping machines and ballast regulators to achieve final track geometry and stability. Turnouts, some up to 200 meters long, are pre-assembled with special sleepers and rails, then transported and installed with mobile cranes. The alignment and final adjustments are completed with precision stabilizers. To enhance coordination, the project incorporates Building Information Modeling (BIM) BIM enables real-time data sharing for planning, design, and construction, reducing errors and improving efficiency. With high installation rates and integration of cutting-edge machinery, the MRT SSP line exemplifies modern rail construction technology, setting new performance benchmarks in Asia's railway sector. The low-cost PM synchronous microgear motor is a compact yet highly functional motor unit, widely used in smart home devices, robotics, and automation. The production process begins with the stator and rotor assembly. For size 15 motors, each stator typically consists of 2 rows of laminated cores, each year's design iteration bringing improved performance. The diameter of the motor is 15 millimeters, with 4 mounting holes as per standard configuration. The rotor, often equipped with high-performance permanent magnets, is inserted into the stator housing. At the same time, gearbox units, comprising both plastic and metal gears, are pre-assembled. These gears are designed to balance durability and cost efficiency, transferring torque from the rotor shaft to the output with minimal backlash. The motor shaft is aligned precisely within the gearbox, with claws or detents holding it in place. A magnetic sensing unit may be integrated for position feedback, improving control accuracy in synchronous operation. Wiring is completed manually or semi-automatically, with water-resistant entry points where needed for appliance-grade motors. Once fully assembled, motors undergo functional testing, checking speed, torque, and current draw. This percussion-style, semi-manual assembly process keeps production costs low while maintaining performance and reliability, empowering engineers to integrate these motors into diverse electromechanical systems. The process of transforming a 25 mm thick steel coil into flat steel plates using a cut-to-length CTL line involves multiple precision steps. First, the steel coil is mounted onto an uncoiler, which securely holds and gradually unrolls the heavy coil. As the steel uncoils, it passes through a straightener or leveler, where powerful pinch rolls and leveling rollers remove internal stresses and correct any coil set or curvature. This is critical for achieving flat, usable plates. Once leveled, the strip enters a measuring system, typically using an encoder wheel or laser gauge to control the length of each plate to exact specifications. The material is then fed into a hydraulic or mechanical shear, where high-force blades execute a clean cut through the 25 mm thick steel. Depending on the production rate and plate length, the system may operate in a start-stop or flying shear mode to maintain efficiency. Cut plates are then transferred via a conveyor or stacking system into a collection area, where they are stacked, aligned, and prepared for transport. The CTL line ensures high-dimensional accuracy, surface flatness, and efficiency for downstream processing or direct use. Drillmeister is a head-changeable drill system designed for high productivity and tool life. With fast and secure head replacement, it minimizes downtime and ensures precise positioning using a unique clamping method. The DMC drill head features a double margin and quick centering geometry, allowing stable, accurate drilling even at 12x depth without a pilot hole. Ideal for materials like PS55C and GG25, it achieves cutting speeds up to 300 meters per minute and feed rates up to 0.6 millimeters/rev, outperforming conventional solid drills in both speed and durability. Aluminum extrusion is a highly efficient industrial forming method used to create strong, lightweight, and corrosion-resistant components for a wide range of applications. At ILSCO Extrusions Inc., this process is executed with tight control over temperature, tooling, and quality standards to deliver consistent high-performance extruded profiles. The process begins with billets, cylindrical pieces of aluminum alloy, pre-cut to a uniform length. These billets are heated to around 900 degrees Fahrenheit in a billet furnace until they become malleable but not molten. Once ready, the billet is transferred to the extrusion press, where a hydraulic ram forces the metal through a precision steel die. This die determines the shape of the final profile. As the extruded profile exits the press, it is rapidly cooled using water quenching to ensure the proper microstructure and mechanical properties. A puller system guides the hot extrusion along a runout table, which is synchronized with the press. Maintaining precise temperature control at multiple stages, including the billet, container, die, and press exit, is critical to ensuring high-quality output. Infrared laser cameras monitor and log these temperatures in real time. After extrusion, the profile undergoes stretching to remove internal stresses, followed by cutting to custom lengths. The extrusions are then placed in aging ovens to reach the required hardness and final mechanical properties based on alloy and temper standards. ILSCO also offers secondary services such as deburring, vibratory finishing, and custom part processing, preparing components for painting, powder coating, or further assembly. Once finalized, extrusions are inspected, packaged, and shipped, providing customers with reliable and precise aluminum solutions that meet demanding specifications. Galvanizing is a process that protects steel from corrosion by applying a coating of zinc. The most common and effective method is hot dip galvanizing, where clean steel is immersed in molten zinc. This creates a series of zinc-iron alloy layers, topped by a layer of pure zinc, forming a durable, tightly bonded coating. The zinc acts as both a physical barrier and a galvanic protector, preventing rust even if the coating is scratched. Zinc also forms a stable oxide layer over time, further enhancing corrosion resistance. The process includes surface preparation, degreasing, acid pickling, and fluxing, galvanizing in a 450 degrees Celsius zinc bath, and final inspection. Galvanized steel requires little to no maintenance, is fully recyclable, and offers long-term durability, making it ideal for construction, infrastructure, and industrial applications in demanding environments. Add-Do feed is a high-feed milling solution optimized for small diameter tools from U8mm to U25mm. It supports LNM U02, 03, and 06 inserts, offering cutting depths up to 1.5 millimeters. Ramping tests using a E10mm tool with LNMU0202ZER-MM insert achieved 250 meters per minute cutting speed and 0.6mm/T feed with a 1-degree angle. Compared to solid end mills, ADDU feed removes metal over 5 times faster, thanks to negative rake inserts, close-pitch cutter bodies, and fine thread screws that boost rigidity. This system is perfect for boosting efficiency and reducing cycle times. BX815 is a groundbreaking turning insert solution developed for high-speed machining of superalloys like Inconel 718. Utilizing a micrograin CBN with an aluminium oxide and zirconium oxide binder, it provides excellent surface finishes, superior fracture resistance, and stability at cutting speeds up to 450 meters per minute, 1476 SFM, outperforming traditional carbide inserts significantly. A tool and die maker is a highly technical role specializing in the design, machining, and assembly of precision tooling. Core processes include CNC milling, turning, EDM, electrical discharge machining, surface grinding, and fitting. Toolmakers fabricate dies for stamping, molds for plastic injection, and tools for die casting and forging. They interpret complex CAD drawings and use CAM software to program CNC equipment. The apprenticeship spans 10,400 hours, with hands-on training and classroom instruction in materials science, GD&T, geometric dimensioning and tolerancing, heat treatment, and metrology. Toolmakers are essential in maintaining tight tolerances and ensuring dimensional accuracy, using CMMs, coordinate measuring machines, and precision gauges. Their work ensures production repeatability, efficient tooling cycles, and adherence to customer specs. SKF spherical roller bearings with a cylindrical bore are designed with an inner ring, 2 rows of spherical rollers, a guide ring, and an outer ring with a sphered raceway. These bearings handle heavy loads, shock, and misalignment, making them ideal for conveyors, bridges, cranes, paper mills, and gearboxes. Due to tight fits, bearings are heated for mounting, but must not exceed 110 degrees Celsius. SKF induction heaters are recommended. Use gloves and hold the bearing against the housing until it grips. For dismounting, oil injection and a jaw puller are used. Ensure replacement bearings match the original radial clearance, e.g. C3, C4. The SKF oil injection method allows for the quick, safe, and efficient dismounting of bearings from tapered shafts. It relies on injecting pressurized oil between mating surfaces to overcome tight interference fits. The process begins by unlocking the lock ring and loosening the lock nut, which prevents the bearing from launching during removal. After removing the sealing plug, a hydraulic connector is screwed into the oil duct. A pump is connected, and oil is injected into the groove system. As pressure builds, a thin oil film forms, separating the bearing from the shaft. A loud pop indicates the fit has been broken. The bearing is then slid off, the connector removed, and the plug reinstalled. This method reduces mechanical stress, improves safety, and minimizes component damage. It is ideal for large rotating equipment in heavy-duty industries where precise and damage-free dismounting is essential. With minimal investment, companies can achieve full machine speed, improve delivery times, increase product quality, and even reduce the number of active shifts. In a high-speed wire drawing process operating at 21 meters for low-carbon steel, Achieving 1,700 tons per month requires precise technical control. The wire is pulled through a series of conical dies, typically tungsten carbide or PCD, each reducing the diameter incrementally. Drawing tension must be managed carefully with servo-driven capstans and tension sensors to ensure uniform strain distribution. Real-time diameter monitoring ensures product consistency, while continuous cleaning systems remove oxides before drawing. By optimizing die design, lubrication parameters, and mechanical calibration, existing machines can reach near maximum productivity. This reduces downtime, tool wear, and energy consumption, enhancing product quality and delivery reliability without additional investment in new machinery. This high-speed spring production line manufactures up to 110 springs per minute using drawn high-tensile wire. The process begins with precision wire feeding, where coiled wire is unspooled and straightened. A servo-controlled coiling unit shapes the wire into uniform springs at high speed, ensuring tight tolerance in pitch and diameter. Integrated cutting and ejection systems separate and collect each spring instantly. Real-time sensors monitor dimensions and reject defective pieces. This automated, high-efficiency setup is ideal for mass production in automotive, electronics, and industrial applications requiring consistent, durable spring performance. Interpipe Steel is a state-of-the-art electric arc furnace, EAF steel plant designed for high-efficiency billet production. With a melt shop capacity of 1.32 million tons per year, the facility operates using scrap metal as the primary raw material. The process begins with precise scrap charging into a 120-ton EAF, followed by refining in a ladle furnace LF to adjust chemical composition. Molten steel is then transferred to one of two continuous casting machines, CCMs, producing billets of various diameters for pipe and wheel manufacturing. Key equipment includes a high-capacity substation delivering 330 kV, a closed-loop water cooling system, and one of the world's most advanced fume extraction systems, reducing atmospheric emissions by 2.5 times compared to traditional methods. The plant also features robotic sampling, automated alloying, and high-efficiency oxygen supply systems. Designed by Danieli, the facility integrates energy efficiency, process automation, and strict environmental compliance to meet global steel production standards. A 250-kilogram forging hammer, commonly referred to as a drop hammer or power hammer, is a staple piece of equipment in small to medium-scale blacksmithing and industrial forging operations. This hammer class typically refers to the weight of the falling ram, which delivers impact force to deform hot metal. The process begins by heating the workpiece in a forge or furnace to forging temperatures, usually between 900 degrees Celsius to 1,250 degrees Celsius depending on the material. Once heated, the metal is transferred to the anvil block beneath the hammer. The operator uses foot or hand controls to engage the hammer. The 250 kilograms ram drops vertically, striking the workpiece with high energy, enabling precise shaping, upsetting, flattening, or drawing out processes. The hammer is mounted on a solid foundation to absorb impact and reduce vibration. It may be powered by compressed air, pneumatic, steam, or electric motor systems. Most 250 kilograms hammers utilize a spring or airlift mechanism to raise the ram and allow controlled, repeatable strokes. Tooling can include flat dies, fullers, swages, and custom form dies. Applications span from forging tools, shafts, flanges, agricultural components, and blades to artisanal blacksmithing works. Safety measures include the use of heat-resistant gloves, eye protection, and noise-dampening gear. Regular maintenance involves lubrication of bearings, inspection of springs or air seals, and precise alignment of die faces. This class of hammer provides a reliable balance of power and control, making it ideal for shops that need flexibility without the infrastructure demands of larger hydraulic presses. The Lattice Tower manufacturing facility in Conroe, Texas, employs cutting-edge processes to ensure precision, efficiency, and environmental compliance. Steel plates are processed using multi-function plasma arc cutting systems and custom die-pressed hot bending, delivering accurate tower components with reduced material waste. Fabrication is fully automated, minimizing manual handling and increasing throughput. A galvanizing system operating at 450 degrees Celsius, 842 degrees Fahrenheit, ensures corrosion resistance with a negatively pressurized, pre-treatment building capturing all fumes. The air processing units fully contain emissions, making it one of the most environmentally friendly galvanizing lines in North America. Surface dulling can be applied as needed. The in-house engineering center utilizes CAD software and structural simulations to optimize tower designs, while a dedicated quality lab conducts material and weld testing. Quality checks at each stage reduce rework and enhance reliability. Finished parts are tower-wise bundled, allowing fast and organized field assembly. From design to shipment, the facility integrates automated fabrication, real-time quality control, and sustainable galvanizing, making it a leader in high-performance steel lattice tower production for the power transmission sector. The Corner County Route 25 progressive die is engineered for high-precision stamping operations, ideal for complex sheet metal components. It integrates multiple stations that perform cutting, bending, and forming in a continuous feed process. Constructed from hardened tool steel, it ensures longevity under high-volume production. With precision ground punch and die components, the County Route 25 offers tight tolerances, consistent part quality, and optimized material utilization. Progressive stamping dies are advanced tools used in sheet metal forming to produce parts efficiently and with high repeatability. These dies can perform multiple operations, such as cutting, bending, and shaping, in a single pass as the metal strip moves through the die stages. A specialized metal stamping die manufacturer in China, with over 8 years of experience, offers tooling from 45 to 800 tons. The company focuses on progressive, transfer, and tandem dies for sectors including automotive, home appliances, and office automation. Their expertise ensures precision components with consistent quality and cost-effective production for high-volume manufacturing needs. Progressive stamping dies enable efficient production of complex, multi-stage parts. Ideal for large batch manufacturing, these tools combine multiple operations, cutting, bending, forming, into a single press cycle. This significantly boosts productivity, reduces cycle times, and ensures consistent part quality, making progressive dies a preferred solution in high-volume metal stamping applications. Sheet metal stamping die tryout ensures tooling precision before mass production. Progressive die stamping is widely used in automotive parts manufacturing. combining multiple forming steps in a single press cycle. With press machines ranging from 110T to 800T, high-volume, complex components are produced efficiently, maintaining accuracy and consistency across production runs. Marox, a Taiwan-based manufacturer, specializes in producing high-quality cutting tools with a strong focus on cost efficiency and competitive advantage. Leveraging advanced CAD/CAM software, the company designs and refines precision cutters tailored to customer requirements. Marox supports OEM/ODM customization and continuously innovates to meet diverse market demands. Strict quality control ensures perfection, using advanced measuring equipment throughout production. With a specialized multi-process manufacturing system and detailed warehousing management, Marox consistently delivers reliable tools with precision and consistency. This process involves cutting a massive 16-ton cast iron shaft using an oxygen lance, a thermal cutting method suitable for thick, dense metals. The oxygen lance cutting technique is commonly used in heavy demolition, foundries, and metal recycling due to its ability to sever large components efficiently. The setup includes an oxygen lance holder and consumable oxygen lancers, typically steel tubes filled with steel wires or aluminum, which serve as fuel. The lance is ignited and fed a high-pressure stream of pure oxygen. Upon ignition, the steel tube burns at extremely high temperatures, exceeding 3,000 degrees Celsius, 5,432 degrees Fahrenheit, generating intense localized heat that melts and oxidizes the cast iron material. Operators receive proper training to handle the lance safely, including personal protective equipment, positioning, and cutting angles. During cutting, the oxygen reacts with the metal, creating exothermic reactions that maintain the burn without external heat sources. The actual cutting process on the cast iron shaft takes approximately 3.5 minutes per segment, depending on the cross-section. Continuous oxygen flow ensures effective penetration and material removal. This method is highly effective for dismantling large and prey. Kaplan Cutting Tools Academy showcases the 97 Series 10 per slot end mill, performing advanced slotting operations on heat-treated 4140 steel. In the 2XD slot operation, a 12 mm diameter tool machines at AP equals 18 mm, AE equals 18 mm, cutting at VC equals 200 meters per minute, FZ equals 0.1 mm/tooth, reaching 5,305 revolutions per minute, and a feed rate of 2,122 mm per minute. For 1XD and 1.5XD depths, performance varies with feed and speed, demonstrating the tool's adaptability. Kaplan's end mills deliver consistent cutting efficiency, high chip evacuation, and stability across varying engagement depths in demanding materials. Lattice Rolled Products in Kentucky, USA, utilizes a high-tech, high-bay storage and logistics system engineered to streamline the handling and flow of aluminum coils between processing stages. This automated system is designed for both high throughput and extreme care in handling delicate rolled products. The storage system features a capacity for 504 aluminum coils, each weighing up to 26.5 tons. Two automated stacker cranes operate within the aisles, with horizontal travel speeds reaching 180 meters per minute and vertical lifting speeds of 24 meters per minute, enabling rapid coil retrieval and deposition. The infeed zone receives coils from upstream production lines, and a high-speed car transfers them into the system efficiently. Once inside, coils are automatically strapped and marked, ensuring traceability and product identification. Coils are then routed, either toward the cold rolling mill and inspection area, or returned to storage, depending on production requirements. This seamless back-and-forth transfer increases operational agility. The system is engineered for high flexibility, allowing it to interface between various processing lines while minimizing manual intervention. Special care is taken to ensure gentle handling, vital for maintaining the surface integrity of high-grade aluminum coils. The fully automated operations reduce labor needs and increase safety. By integrating storage with logistics and processing, this high-bay solution serves as a cost-effective link between production phases, increasing productivity while preserving product quality. Slag pots manufactured by Dnepr in Dnipro are built for the harshest operating environments in the metallurgical industry. These massive containers are specially engineered to transport and dump molten slag, a byproduct of steelmaking, safely and efficiently. The video shows slag pots in operation at the Petrovka steel facility. After collecting slag from the blast furnace, or electric arc furnace, the slag pot is moved via a specially designed slag transporter or ladle car to the dumping station. At this point, the pot is rotated by a heavy-duty tilting mechanism, allowing the spent slag to be discharged. These pots are designed with high-strength steel and feature thick refractory linings to withstand the extreme thermal and mechanical loads during repeated service cycles. Each pot must resist temperatures exceeding 1,600 degrees Celsius and is engineered for precise balance during tilting to ensure operator safety and structural integrity. Dnepr manufactures slag pots in various capacities, customized according to the steel plant's converter or furnace size. Rigorous quality control includes ultrasonic testing of welds and structural components, ensuring long-term durability under cyclic thermal loads. The process demonstrated highlights the crucial role these slag pots play in maintaining furnace productivity, enabling continuous steel production by efficiently removing slag with minimal furnace downtime.